now we have all the pieces in place to describe an ARIMA model. We've seen differencing, and we've seen autoregressive models, and we've seen moving average models. And when you put these three things together, you have an ARIMA model. The word ARIMA comes from AR for the autoregressive part of the model, where you have lagged observations as your inputs. The I comes from integrated, which is the opposite of differencing. So that's where you difference your series to make it stationary. You fit the model and then you undifference or integrate. And then the MA part is the moving average part of the model. So you put these three things together, AR, R, I, MA, and you get an ARIMA model. Unlike the exponential smoothing models that we saw in the previous chapter, ARIMA models don't have the same nice interpretation in terms of things like trend and seasonality. On the other hand, though, it can capture a huge range of time series patterns. And in some ways, some types of series you can only model with ARIMA models. You couldn't model them with ETS models. So let's write out the full model then. So this is without the differencing part. So this is just autoregressive and moving average together. And we have on the left-hand side the variable you're interested in, and on the right-hand side all the lagged AR parts up to lag P, and all the lagged MA parts up to lag Q. And the AR parts have these phi coefficients like this, and the MA parts have these theta coefficients like so. That's very standard notation. Pretty well every book will use the same notation. So your predictors or your inputs to the model include both lagged values of Y and lagged errors. And there are conditions on the phi coefficients and the theta coefficients to make sure the AR part is stationary and the MA part is invertible. So when you write it like this without the differencing, you call it an ARMA model, ARMA model. When you put the differencing in, it's an ARIMA model, ARIMA. And simply it means that you've done some lot of differencing before you then go ahead and fit an ARMA model. And it can be more than one lot of differencing. So you say that the difference series, having differenced at D times like this, the difference series follows the ARMA model. The original series follows an ARIMA model. So the way we normally write this is an ARIMA PDQ model, with a P says how many AR terms there are, the D how many differences you used, and the Q how many MA terms to include in the model. And those things can be zero. So if they're all zero, so you've got no AR parts and no MA parts and no differencing, then your model is simply going to be, if you write out the equation for the model, it's simply going to be YT is equal to error. So you write it like this. Where's my pen gone? Over there. So you write it like this. YT is equal to error. And so it's white noise. If you've got a random walk model, then you've got some differencing, one lot of differencing. So here in the notation, there's no AR part, there's one difference, and there's no MA part. So you can write the model as the difference series equals, and on the other side, there's no AR part, there's no MA part, so you just have an error. And that's sometimes called a random walk model because you can rewrite it as YT is equal to YT minus 1 plus some error. So every observation is wherever you were last time plus a bit. So it's like randomly walking through the space. You jump randomly at each step in whatever direction. A random walk with drift is similar, except you have a constant as well. So you've got a difference is equal to a constant plus some epsilon. And so that gives you the random walk with drift model. And if you've got just AR parts but no differencing and no MA parts, then you sometimes just write it as ARP. So you can see that if you drop components of the model, then you can drop the parts of the notation as well. So an ARIMA P00, because you've got a 0 here and a 0 here, you can drop these bits and just write it as ARP. And similarly for an ARIMA 00Q. So they're all special cases of this model class that we've seen before. Okay, so now let's look at backshift notation for these models. So if we write out the model, if we take the model that we saw in back here, where we've got it in subscript notation in the top box there, this model here, and if we write it out in backshift notation, then it looks like this, that first equation there. And then you combine terms, combine all the y terms, combine all the epsilon terms, and here it is in backshift notation like this. And that is usually the most convenient way to write down an ARIMA model or an ARIMA model. It makes it easier to see the various components. So to take a specific example, if we had y is equal to 1, sorry, if we had d is equal to 1, p is equal to 1, and q is equal to 1, so you've got one lot of differencing, one AR term and one MA term, then you can write it down in backshift notation like this, where the differencing part of it is here, and then you apply the AR1 part of it, which is 1 minus phi, 1 times the operator b, and the MA part over here, like this. And we start to build up these terms now. If you expand that equation, the backshift version, into the subscript version, then it becomes harder to see what's going on. So they're exactly the same thing, the equation here in backshift notation. But if you expand out, multiply these guys together, expand them out, apply them to y, and apply this part here to epsilon, and then rearrange so y is on your left-hand side, you get this equation. And you can't really tell from that equation that you've actually got an ARIMA 111. It's not obvious at all that that's an ARIMA 111. You might be thinking, oh, that looks like a p equals 2 because I've got 2 lags here. So you might be confused and think that's an ARMA an ARMA 21, p equals 2, q equals 1. You'd be wrong if you thought that. The reason is that this doesn't satisfy the stationarity conditions for the coefficients when you write it in this form. You write it in this form up here, and it's more obvious that you've got an ARIMA 111. There's actually 2 different ways these models get written in various textbooks. There's the intercept form, which is what we're using in this book and what Fable uses, which is the top equation here. So you apply all of your backshift operators to your y or your differenced y. You apply all your backshift operators to your epsilon, and you put in an intercept C like that. The other form, which is popular in some books and in other packages in R, not the Fable package, is the mean form, where you first of all subtract the mean of the difference data and then apply the operators. These are equivalent, but just a different notation, and the output from the functions, you need to be careful which one of these you're using. As I said, Fable uses the intercept form. You can go backwards and forwards between them. The C here is equal to mu times 1 minus all of the sum of all of the AR coefficients. So that's just in case you need to see the other form. Okay, let's try this out on some data. So here I have Egyptian export data from the global economy dataset. I've filtered out just the Egyptian part of the data, and I'm plotting the data for exports. So it looks like you've got a little bit of cyclic behavior going on like this. And you'll remember from when we talked about autoregressive models that you can get cyclic behavior in an autoregressive model, provided P is at least 2. One of the things an autoregressive or an ARIMA model can do that an ETS model can't do. ETS models can't handle cyclic behavior in the data, only seasonality, whereas an ARIMA model can handle both. Okay, so in Fable, we can pipe that into the model function and say we want to fit an ARIMA model to the exports data, and it automatically chooses a model. Later in this chapter, we'll see how the automation of it happens, It's similar to ETS, it's just minimizing the AICC. In this case, it comes back and it says an ARIMA 201 with a constant is your best model. So, and it gives you the various coefficients. So to write that out in our notation, there's no differencing here, so it's easy enough to write it in subscript notation. The constant here is our intercept, that goes there. The AR1 part, phi1, the AR2 part is phi2, and the MA1 part is theta1. Then the sigma squared, which we get, we get rid of all the lines, the sigma squared from here is the variance of the residuals, or the square root of that is the standard deviation of the epsilons. So that's what's coming in here, like this. Okay, look at the residuals of that like we did for other models, and you can just check that this looks like it's behaving appropriately. It should be white noise. And so it's plotting the residuals, the epsilons or the estimated epsilons here, the ACF and the histogram, and everything looks fine. That looks like it's centered around 0. There's no obvious patterns in the time plot. All of the spikes are well inside the blue line, so that looks like white noise. This is nothing particularly weird going on, so I'm willing to believe that's approximately Gaussian. If I go ahead and produce some forecasts by taking the fitted object and piping it into the forecast function, you can see that my forecasts actually have picked up the cyclic nature of the data, and it's picking up the increase part of the cycle and then the decrease, although the prediction intervals are quite wide because cyclic behavior is really hard to predict, and so it's saying that it's, you know, could actually be anywhere in this region. So that's an example of an ARIMA model. Let's just talk a little bit about some of the features of the model to make sure we understand what all of the different parts are doing. So for long-term forecasting, the most important parts of the model are actually whether or not you include a constant and how many differences you include. The P and the Q are only affecting the short-term part of the forecasts. The C and the D are affecting the long-term part of the forecast. So if they're both 0, if C and D are both 0, so there's no intercept and there's no differencing, then in the long run, your forecast will go to 0. So your point forecast will be trend towards 0, will converge to 0. If you don't have a constant, but you do have one lot of differencing, then the long-term forecast will converge to a constant, but it will not be 0. And if you don't have an intercept and you have 2 lots of differencing, that is, you've differenced and then differenced again, then your long-term forecasts will follow a straight line, will converge to a straight line. If you have an intercept in the model, then the behavior is different. If you have an intercept in the model but no differencing, then your long-term forecast will converge to the mean of the data. So you're assuming it's stationary, so in the long term, you're expecting the forecast to behave like what you've seen historically, so your long-term forecast will converge to the mean of the data. And the long-term prediction intervals will actually converge to the based on the standard deviation of the data. If you've got a constant but one lot of differencing, then the long-term forecast will follow a straight line. And if you've got a constant and 2 lots of differencing, which we don't recommend, the long-term forecast will follow a quadratic. That's why we don't recommend it, because you don't generally want quadratic trends in your forecast period. So notice that if you add a constant, then basically the behavior behaves like you've got, let me explain that better. So if you've got no constant and d equals 1, it goes to a non-zero constant. So it's like that. If you've got no constant and d equals 2, it behaves like you have a constant and d equals 1, a little bit like that, because they're both following straight lines. And there's no equivalent of quadratic if you don't have a constant. What about the variance? Well, the bigger D is, the more rapidly the prediction intervals will increase in size. So if D equals 0, the long-term forecast standard deviation will be the standard deviation of the historical data. If D equals 1, you're going to get this, it's going to increase. If D equals 2, it's going to increase even more rapidly. It's sort of going to blow up like that. For cyclic forecasts, you need P at least 2. And some other restrictions on the coefficients. You can't get cyclic behavior if P is 1 or 0. If P equals 2, then you need the additional constraint on the coefficients that phi1 squared plus 4 phi2 is less than 0. And then you're going to have cycles in your forecast, and the cycles are going to be of this length. Given by that expression. So we saw cycles in the model for the Egyptian exports data, and if you check the coefficients, you'll see that in fact this is satisfied, and if you work out what this is by plugging in the values for the coefficients, you'll see what the average length of the cycle is. Okay, there's another type of autocorrelation that we use once we start working with ARIMA models that's useful to know about. It's called partial autocorrelation. And just like autocorrelation, it's measuring the relationship between observations k periods apart. So an autocorrelation says, well, what's the correlation between yt and yt minus k? A partial autocorrelation says, what's the correlation between yt and yt minus k after you take out the effect of all of the intervening lags. So if you think about what's going on a timeline, let's just draw a little timeline here. And I'm sitting here at, I'm sitting over here at time t. So just so don't get confused, that t over there means time. This is a particular time t, and this is time t minus k over here. Now, if there's one-step correlation, then the observation at lag t is going to be related to the observation at lag t minus 1. That's if there's autocorrelation at lag 1. And that's going to be related to the correlation at the observation at time t minus 2, and so on, all the way back till you get back to time t minus k. So if you have one lag autocorrelation, you can induce k lags of autocorrelation simply because of the connections. So the idea of a partial autocorrelation is to take out those connections, to say, okay, even though there might be a one-step correlation and there might be a two-step correlation or a three-step correlation, if I can remove the effect of those, is there anything left that's connecting t with t minus k, taking out the effect of all of the other ones? The way you compute this is you simply do a regression of yt against the last k values, and it's equal to the estimate of the kth coefficient. That makes sense, really, because if you think about regression, every coefficient is the effect of that variable having taken out the effect of all the other variables. So the coefficient of yt minus k is the effect of yt minus k on yt, taking out the effect of all of the other ones. And that's called the kth partial autocorrelation coefficient. It's the last one in the regression. So if you're going to estimate all of these partial autocorrelation coefficients for different k's, you've got to fit all of these different regressions. There's actually more efficient algorithms that don't require you to do all of those fits, but that's conceptually at least one way to think about it. So varying the number of terms on the right-hand side of this equation will give you different values of k and therefore different alpha k's, partial autocorrelation coefficients for different lags. Of course, when k equals 1, there's nothing in between, so there's nothing to take out. So the kth partial the first partial autocorrelation coefficient is the same as the first autocorrelation coefficient. Alpha 1 is equal to rho 1. It also has the same critical values. So the blue lines, when we plot these, are going to look exactly the same on the PACF graph as they are on the ACF graph. And one way to choose whether you've got an AR, choose the P in an AR model, is to find the last significant lag when you plot these things. So let's look at the Egyptian exports data again. And here I've filtered out the Egyptian data, and then I'm doing the ACF plot and a PACF plot. So the PACF plot's just done with the PACF function. And this line of code produces the left-hand side graph. This line of code produces the right-hand side graph. Now remember what the last line of the previous slide says. The last significant or partial autocorrelation coefficient indicates the order of an AR model if you have a pure AR model. So you look at the PACF, you say, what's the last significant spike? So you go from the right-hand side, you're looking for a significant spike. The first one you find, which is the last significant one, is this one. So that suggests that an AR4 might be a reasonable model for the Egyptian export data. You can only use this trick if you have a pure AR model. You can't use it for mixing MA and AR terms. Now, previously, we automatically identified an ARIMA 201 model for this data set, back a few slides. This is saying that an alternative model might be an AR4 model. So we have two possible models, the one that's automatically identified and the one we've manually identified from this graph. If we go to R and see how well those models fit, let's have a look. So we take the Egyptian data, and I'm going to fit these two models, AR4 and the one that's automatically chosen. So I fit an AR4 model by just saying PDQ, P equals 4, D equals 0, Q equals 0. So that's fitting an AR4 model or an ARIMA 400 model. This line's, I'm not specifying anything, so it's going to automatically pick a model. And then if I use the glance function, I can have a look to see what the fit looks like in terms of ARC, and you can see that the automatic model is slightly smaller than my chosen model. Just 1 to the third, ignoring the decimal places that are not shown here. So my guessed model is actually pretty close to the best available model that's chosen automatically. But as I said, you can't use that trick in choosing a model if you're going to mix up AR and MA parts. You can only use it to choose the AR part. This is another function for easily creating the ACF plot and the PACF plot. You don't need to do them separately like I did on the previous slide. You can just pipe the data into GGTS display, say which of the series you want to plot. And if you say plot type is partial, then it will do a partial autocorrelation function plot over here. Has a time plot at the top and an ACF plot on the bottom left. So it's a quick way to see those three plots all together. Other thing to notice about this, which you probably saw back here as well, is that this is looking sort of sinusoidal. So that's typical of cyclic data. It's also typical of seasonal data, but we know this is not seasonal because it's annual data. So it's typical of cyclic data, and it's telling us that the cycles are around about 14 years on average apart, because the spike there is at lag 14. In fact, you can interpret the PACF and ACF for pure AR models and for pure MA models by looking at those sort of things. So if you have an AR1, then you tend to find the autocorrelations look like this. They decay exponentially. So they look like that, where that decay looks like that. And on the PACF side, because it's an AR1 model, you should just get one significant spike at lag 1 and then 0 for everything else. They might be negative or positive, but there's one significant spike. So that's typical of an AR1 process. And algebraically, you can write the autocorrelation function like that, and the partial autocorrelation function like that. If you've got an ARP process, you tend to find the ACF is dying out exponentially like I just drew. Let me draw it again. It tends to be either like this, where it dies out exponentially, could be positive or negative, or you have a damped sign pattern where you have this sort of behavior. Let me do it like this. So it's sort of it's a sign pattern, but it's getting smaller as the lags increase. And then on the PACF side, so that's the ACF up here. On the PACF side, you're going to have spikes in the PACF up until lag P, and then nothing significant after that. So one way to pick an ARP model is to see, does the ACF look like one of these two shapes? And is there a significant spike at lag P in the PACF, but not beyond it? Then you've possibly got an ARP model. That's in fact what I did when we saw these graphs. Got a sinusoidal behavior here. This is doing this sort of thing. Sorry, bad drawing. And this is spike at lag P and nothing else. Classic AR4 behavior. Turns out that's not the best model. We had a better ARIMA 201 model, but it's a good model. It's a decent model. If you've got a pure MA model, like an MA1 or an MAQ, then it's actually just the reverse. The PACF tends to be exponentially decaying, and there's a significant spike in the ACF. So the ACF looks like one spike at lag 1 for an MA1, and then nothing. And the PACF, let me do it the other way around. The ACF, I'm going to do it on the negative side because that's much more common. The ACF looks like that, and the PACF looks like this, where it's decaying like so. That's typical MA1 behavior. If you've got an MAQ behavior, then it's like the ARP, but with the PACF and the ACF reverse. So you get the exponential or damped sine wave on the PACF, and you get the ACF having significant spikes up to, and possibly include up to the Qth spike, but not necessarily all the spikes up to the Q. The last significant one is the Qth spike, and then none beyond that. So yeah, so the ACF and the PACF are quite useful ways for picking pure MA models or pure AR models, but you can't use them to pick a mixed ARIMA or a mixed ARMA model. For that, we need other tools, and we're going to do that in subsequent sections.